Hey Copenhagen, hey DKNOG. This is Thomas from Flex Optics. Sadly, I can't be on site today. I'm pretty sick, so I hardly made it to the office now to make that presentation, but I can't travel. So I'm very, very sorry that I can't join you. So I do the talk remotely. I'm pretty well prepared. Do you see my, by the way, I'm gonna share my screen now. So you should be able to see my screen now. Here we go. Okay, I caught a flu, so I will blow my nose sometime. But I try to mute the microphone. But I'm well prepared. Looks like this here. Okay, here we go. To get some feedback from you guys as well at the beginning, or while I do the presentation, because I can't see you, I only see this nice icon there. I do have some questions. A pretty simple one, like we can do a trial now. So, for example, when in the field of math, what is 2 plus 2? And you should answer, because then I get a little bit of feedback. So, what is 2 plus 2? Perfect. I heard that. Great. You're on. Okay, let's start. 400 gig. That's the presentation today about it. I did this presentation a while ago, or started with it, because the 400 gigabit transceivers are upcoming now, and they are ready to launch the market. But there will be some slightly changes compared with 100 gigabit, and that's the main comparison now in this talk. So taking the knowledge from 100 gigabit, which lessons were learned when we move towards 400 gigabit. At the beginning, I do have a theory part, and then later on, I move on to the hands-on one. I gave that talk already on a RIPE meeting, and Aaron from 6Connect came to me afterwards and said, hey, Thomas, you should rename that presentation. Better call it from Cyclops to Triclops. Why is it so? You will see later on now in the theory part. So let's start straight ahead, and that's pretty simple physics, or basically physics or computer science knowledge. So when we have a rectangle signal, this shape here, this rectangle signal goes through two events. You have a low event down there and a high event up there. With these two events, you can represent one bit. That's one important thing to know, and I think pretty much everyone is aware. The second one is when I talk to network engineers, and that's also the practical attempt here. Some people may know the term of an eye diagram, and when you ask deeper and ask, hey, what is an eye diagram? The answer is, yeah, I know an eye diagram, but I don't know the innards. So I also want to try to explain a little bit what is the important part of an eye diagram and why it is so important. So in general, the important thing, and that's pretty easy, you want an open, clear eye. That's a really important thing on an eye diagram. But how do we get there? So when we have our signal here, for example, and in a sequence of 3, so starting with a 0 event, a low event, going up to a high event, and then going down to a low event. So we got 0, 1, 0. That's one combination. So we have 1 bit in 3 different signal states, basically, or going through 2 events. So when we do the math, and that's now a math question, what is 2 to the power of 3? Okay, I'm still on, I hope so. So the answer is 2 to the power of 3 is 8. So looking at those 8 states, let me go back. No. Okay, you can still hear me? No. Or I'm muted. Okay, I move on, unless I hear something. Let me check here. Okay. Okay, let's move on with the presentation. So we have those 8 different states, starting from top left corner 010, going down on the right left corner 110. And when we overlap all of these 8 states, we get something which looks like we see down there on the right corner. It looks pretty much like an eye now. But what actually makes an eye and eye diagram is when we look up there, because that's an actually eye diagram measured from a 100 gigabit transceiver, is the shape in the middle. This shape is really important because our signal, it never should cross that shape in the middle, because if it would cross that shape, we would have an issue on the receiver side, because what we see here is a transmitter side, and the receiver couldn't determine between a high or a low signal, for example, if the signal would go cross in the middle. So it's really important to determine for a receiver that the eye is clearly opened and does not cross that shape in the middle. So this shape is really important to make an eye diagram. As I said, a 100 gigabit transceiver measured with a speed of 25 gigabaud. So what we really want to avoid is a dodgy eye. A dodgy eye looks like this. Yes, I'm not always sick. That's also me playing ice hockey. And yeah, dodgy eyes we want to avoid. I heard something. Am I back? Okay, so there was a huge break now in the middle. Am I right, or did you hear everything? Perfect, perfect, great. Okay, I move on. Thank you very much for that feedback. So when we move on now on the for when we look towards 400 gigabit and looking backwards to our initial rectangle shape with the high and low event. So when we do now add 2 intermediate events into our rectangle shape, so we have now low, H1, H2, and H3, so we have 4 in total. We can encode basically in one signal 2 bits. So that's pretty helpful. How does this look like? It will look like this monster here with 3 eyes. This monster is called pulse amplitude modulation, or 4-level pulse amplitude modulation. Also, Yisheng Wu, the previous talker, mentioned it in the 5G talk. So what is so special about PAM4? We have the same frequency, but now we have those intermediate steps. And even now, it's even more interesting for the receiver, or even more important for the receiver, to have a clear eye on each level, that it can determine between those intermediate steps. Because otherwise, if he can't level that out, he can't determine if it's H1 or H3 or H2. And each event here can represent basically 2 bits, either 00, 01, 10, 11. And just with the fact of the modulation, we now doubled the data rate. We kept the frequency, but we doubled the data rate. And that's one key component within 400 gigabit to increase, to get there, basically, to get from 100 gigabit up to 400 gigabit. So when we do the math now, and I do it, so you don't have to do it, we are at 200 gigabit now, just due to the modulation part. When we move on here for the hands-on section, I got a question on the medical in the medical science section. Are you still awake? Are you still there? Perfect, perfect. Okay. Let's do some recap on the 100 gigabit. 100 gigabit, when we open up a transceiver, we got an electrical side on the left side and an optical side on the right side. Basically, we have that on every transceiver. It doesn't matter if it's 100 gigabit or 10 gigabit or 1 gigabit. But the special thing at 100 gigabit transceivers, at least at the latest generations, when we talk about the form factor QSFP-28, we had 4 times 25 gigabit electrical driven. So the host was driving 4 lanes with the speed of 25 gigabit. And this 4 lanes electrical were driving, or did drive, an optical engine with 4 lasers and 4 receivers, even running at 25 gigabit. Now for the next generation, and the 400 gigabit ones with PAM4 modulation, and we are still missing that, another 2 times coming from 200 gigabit now to 400 gigabit because we have the PAM4 modulation, which doubled the data rate. And how can we quadruple it now? Oh, well, we increase the amount of electrical lanes. So the host now drives 8 times 50 gigabit. And keep in mind, the frequency is still lowered, but we got 50 gigabits on each lane because of PAM4 modulation. And each lane is driving an optical engine at a speed of 50 gigabits. So we have 8 lanes, 8 lasers, 8 receivers. That's going to be somehow the first generation. And when there is a first generation, there will be a second generation. And this first generation is mainly the technology which will be used for multi-mode transceivers, or multi-mode 400 gigabit ones. Now, the second generation is mainly targeted for single-mode transmission. And here you see the major difference. So the electrical side is still running at 8 times 50 gigabit, but there is a gearbox now placed on the electrical side. A gearbox is basically a small ASIC, a chip, which takes those 8 lanes, combines it, increases the frequency of each lane to 100 gigabit basically, or this time 50 gigabaud, and runs out 4 lanes with a speed of 100 gigabit. And these 4 lanes then drive optical engines, transmitters and receivers, 4 pieces each of them. So there might be the question now and say, well, hey, why do we place a gearbox? It's a chip, it's expensive. Why don't we just increase the frequency on the electrical side? In theory, this would be possible, and in practice as well, but no one want to pay for that, because we are still talking about pluggable modules, and the main target is to make it as small as possible for the lowest price possible. So when you would increase the frequency on the electrical side, you couldn't stick to regular PCB material any longer. You need something like ceramic or Teflon to get these speeds transported on an electrical PCB. And the longer the traces are, the more difficult it gets because it's really high frequency. Place a chip there which does all this high frequency stuff and have really short traces here in the middle. Now coming to the real hands-on, when we talk about transceivers itself as pluggable transceiver, and I'm pretty sure every one of you are familiar with the QSFP-28. That's the well-known representative for 100 gigabit transceivers. Now for the 400 gigabit one, there will be either QSFP-DD, which is somehow the successor of QSFP-28, and there's another one called OSFP. And the sizes, which you can see here, the proportions are pretty much how they will be later on. What is so interesting about QSFP-DD? The QSFP-DD port itself is backwards compatible to QSFP-28. It's pluggable. So you can plug in a QSFP-28 into a QSFP-DD slot. So you can either run a 400 gigabit transceiver in that slot or a 100 gigabit transceiver. And how is it done? Well, the physics are pretty much the same beside the length. So QSFP-28 has a length of 70 millimeters, and the QSFP-DD 75, the portion which is inside of the switch. That's important here. So this arrow is not correct. Now, the QSFP-DD is slightly longer and has a second row of connectors. So when you plug in a QSFP-28 into a QSFP-DD slot, yeah, guess what? Only the first connector row will connect. And when you plug in a QSFP-DD into the same slot, both rows will connect and all 4 lanes are connected. For the OSFP, it's a totally different form factor. It's way bigger. It has an interesting part in there, the integrated heatsink, which we will talk later again when we come to the power consumption. Power consumption is an important thing. And you might wonder, hey, why do I combine our power consumption with the size? Well, when you look at the definition, what is allowed to produce as a transceiver, we have a portion of 35 millimeter, which is allowed to stick out of our switch or router. And these 35 millimeter become later on really important for heat dissipation and power consumption. And you might remember back in those days where 10 gigabit DWDM was quite new, 7-8 years ago, the first DWDM SFP pluses had those huge heat sinks in front. And this also will happen now for QSFP-DD. So the bad news are, yes, there will be a big portion looking out of your first front unit, and you better take care how far away is your first rack unit or mounting unit to the front door, because otherwise you can't close the front door any longer of your rack. Now, to the power, as I said, we come later on. What will be connected now to a QSFP-DD or an OSFP, or in general to a 400 gigabit transceiver? And that's quite interesting. There will be somehow new applications possible. For sure, we can back-to-back connect 400 gigabit to 400 gigabit. That's no rocket science, and everyone assumes that. But with the design of those two form factors, we have the ability to do all, which we are also familiar from 100 gigabit or 40 gigabit. So we can now do 4 times 100 gigabit breakout mode, either break it out to a QSFP28, but keep in mind that's not the QSFP28s which we know so far. It's the same form factor, but it will be newer ones which run on a single lambda at a speed of 100 gigabit, because the current ones we have run at 4 times 25 gigabit. With 4 waves, and this one will then run on 1 wave with 100 gigabit. So it's basically technology taken from a QSFP-DD or OSFP and squeezed it into a QSFP28 housing. Newer form factors also will come up on the smaller ones. We got the micro QSFP or an SFP-DD, which is the successor of SFP28 or SFP+. It doesn't matter if it's QSFP-DD or OSFP, how you're gonna interconnect them with each other. This will be equal for all types of application. Now, looking at this breakout scenario, and there's one big lesson learned from the 100 gigabit development is the type of plugs. So you might remember there is this MPO plug mainly used in the multi-mode environment, and when you interconnect 100 gigabit or 40 gigabit on SR4 with each other, you can also break it out to 4 times 10 gigabit and have these breakout cables on the other end with 4 times LC duplex. This also will be part for 400 gigabit. But there are new movements ongoing, for example, from SENCO. It's not standardized yet, this type of plug, but they had a great idea. So what SENCO did, they said, hey, we take a type of an LC plug. So we take the benefits of an LC duplex with the nice ferrule of 1.25 millimeters diameter and the simplicity to clean it, but we make it cascadable. And how does this look like? So it's a cascadable plug. So you can plug in either 1, 2, 3, or 4 of them, and you can even release a single piece. And that will be a big advantage compared with an MPO, because when you look in today's installations doing breakout mode at 40 gigabit with 4 times 10 or at 100 gigabit with 4 times 25, when you unplug that MPO plug, all 4 lanes will go down. With that SN plug, this won't happen, because this nice matrix over there, which is a nice drawing, gives you the capability to build a full mesh on the transceiver side itself, and you can even unplug a single span. That's quite helpful. Well, we'll see how it goes, if SENCO can bring it into the market, and how the market will adapt it, and how the standardization will go. It's not standardized yet, but the TIA, who is in charge of the standardizations for cables and the plugs, they have it on their proposal and for the upcoming meetings. So we will see in this year where it will go, and also if transceiver manufacturers will jump on that bandwagon to say, well, that's a great idea, that we have single links break out from that 4 times 100 gigabit, for example. So another lesson learned when we are at standardization is when we look at the IEEE. So IEEE is basically taking care on the electrical side and also what is happening up to layer 2. Doing the recap again on 100 gigabit, there was mainly only looking at single mode now and not multi-mode. There was only standardized LR4. So 10 kilometers, each lambda had a spacing of 5 nanometers. It was standardized. But technology-wise, other things were also possible. We got either CWDM, so we got 20 nanometer spacing, a broader spacing of the lasers, or even the parallel single mode transmission part, so the typical breakout mode, 4 times 25 gigabit. But it was never standardized by IEEE. But the industry produced it, and the industry, or we, the network community, adapted and said, hey, that's a great thing. But when there is no standard, it's always difficult to implement it. And look at your exchange point, the maturity of exchange point. They offer you a 100 gigabit interface on LR4. They don't offer it on CWDM4 or CLR4. And that's one big lesson also was learned when the 400 gigabit was defined now by IEEE. They said, well, we need some new standards for that shorter reach within data centers and for interconnects up to 2 kilometers or 500 meters. So starting with the 500 meter breakout, that's the DR4 now, and that's also where the SN plug from Senko comes into game. So you can break out 4 times 100 gigabit now, and you get a standard. The second one is FR4, and it's the well-known CWDM4. And why is it so important to have their standard? Because this technology is way enough within a data center up to 2 kilometers, and it's way cheaper to produce than LR4. And for sure, LR4 is still there, doing up to 10 kilometers. Now, that's from the standardization part. Now, again, lesson learned when we look at power consumption. I think that's one of the major things I see at 400 gigabit, which was learned. 100 gigabit transceivers, the old, which even phased out now, like CFP, CFP2, and CFP4, they had the target to carry a lot of power consumption. Yes, this was there, but they never made it into the mass market that well. The mass market was QSFP28, but there we had only a power consumption of up to 5 watts. Now, in general, we would think power consumption up to 5 watts is great because we want to save the environment and we want to save power. Yes, check, I believe in that. But on the other side, the more technology and like DSPs or processors you want to stick into a transceiver, the more power you generate, or the more power you consume, the more heat you generate. And that's a big issue because you have to get rid of that heat. So, and that's one big drawback of 100 gigabit transceivers in the QSFP28 form factor. There's a lot of technology out there which we could squeeze into that form factor, but we could never get rid of that heat, although if we could feed that power in. And this was done at QSFP-DD and OSFP in the definition phase to say, well, we need a form factor at 400 gigabit which can carry up to 12 or 15 watts of heat dissipation to drive newer things in a transceiver. I come to those newer things on the next slide, but even this landmark of 15 watt, although it's standardized, isn't enough. We see now movements in the lab environment that we can drive 20 watts in a QSFP-DD. And how does this happen? You might remember those 35 millimeters on the previous slides where I showed the portion which sticks out of your switch. You put a huge heat sink there and you optimize the fan setup of your switcher router that is a lot of air is sucking through that heat sink, then you can run a QSFP-DD on 20 watts. If you want to have a look there, Cisco did some trials in the last couple of days, and they also published that on their blog. Just Google for QSFP-DD 20 watts and Cisco. I'm pretty sure you will find that blog entry. And that's pretty great, seeing this movement. Now, why do we need such a lot of heat dissipation? And that's, I think, the greatest movement for 400 gigabit is, yes, this issue of seeing at 100 gigabit having transceivers capable handling 10 kilometers, maybe 25 kilometers of distance, but that's the end of the game. Having seen that issue, the 400 gigabit standardization and also the people who design these form factors said, we need a way to build in, again, ZR technology so that we can reach 80 kilometers or even beyond that. Back in those days, with 10 gigabits, we had that capability. Now with 40 and 100 gigabit, we didn't have that capability. And the main driver was the power consumption or heat dissipation. Now, having 20 watts or have the possibility to run a QSFP-DD on 20 watts or an OSFP, you can build in coherent technology into a pluggable. And this coherent technology or coherent DWDM is mainly done with a digital signal processor. And this one needs power and generates heat. And when we can integrate this type of chip, then we can have also 80 kilometers ZR. And that's pretty realistic to do so. Yeah. Finally, a networking question. When is beer time? Well, right, 6 p.m., perfect. That's so far from the 400 gigabit world what I can say. I have seen the first trials of OSFPs done with Arista. They ship out the first units already to their big customers. I haven't seen it from Cisco yet. That's what I know so far. I think 2019 will be damn interesting what will be happening in 400 gigabit. From my side, I can say we will keep an eye on it, and I think there will be pretty much a lot of work for us to do to integrate everything into the Flexbox, to change the configuration of the microcontrollers, because they still will be in those transceivers anyway, to do all kind of stuff to get them up and running in all kind of gear. Thank you very much, and I hope I catched up a little bit time so that we are not running late for beer, at least you. Are there questions?
Yeah. Thomas, can you hear me when I use the microphone?
Perfect. I can hear you clear and perfect.
Do we have any questions? I think they might be waiting for beer, Thomas. They're very quiet.
That's all right. That's all right. Oh. Enjoy the rest of the DKNOG and enjoy the beer later
Thomas,
on.
You will be giving your presenter gift to Fergus, so if any of the candy is missing, you know who to blame. But,
that's true.
A big round of applause for Thomas, please.
Thank you very much.